Okay, guys, today we are going to review transformations with parent graphs. Uh, First thing I'm going to do is go over all the different parent functions that we had learned. Well, maybe not all, but most of the parent functions you've ever learned up until this point of Math 3. So let's start with the first one right here. We have number one, f of x equals absolute value of x. The name of that function is absolute value. The shape it makes is a V shape. The function is the parent, hence its key point is at the origin, and then there is no scaling up of this, so we have a point one to the right, one up, one to the left, one up, and then it's going to be basically a bent line. You can see it's supposed to be a line because it says x, but then the absolute value takes anything that was on the negative side and makes it now positive. That's our V shape. Next one we have here is x squared. That was known as a quadratic function. Shape is a parabola or a U shape. Again, the vertex is at the origin. Go one right, up one, one left, up one. So how is this guy different than this? Because it's squared, its curve wants to accelerate faster and faster. Over here, if we were to plug in x equals 2, we would get 2. Here, if we plugged in x equals 2, 2, here we would get 4, because 2 squared is 4. Parabola. All old stuff you've seen before. Next one we have is square root of x. It's called a square root. Its shape was half, sideways, parabola. We decided to call it a eyebrow. And vertex is at the origin. If you went one to the right, square root of 1 is 1. Goes like this, but instead of accelerating fast, it accelerates slow. And that's because you would have to plug in 4 before you ever got up to 2. Notice the square root of 2 was like 1 point something. Square root of 4 equals 2. That's that shape. Also, notice there is no left side. This has a limited domain because you can't take the square root of negatives in the real world. All right, our next function down here is f of x equals x. Let's slide this up. This is a linear function. It makes a line. That's why it's called a linear. Goes straight through like this. The most basic function, the first one you ever learned how to graph. Next up is x cubed. That's known as a cubic. Its shape is what we called a noodle. Remember, if you look at basic functions like x squared, x cubed, you can tell its end behaviors based on whether the degree is odd or even. Odds have opposite end behaviors, evens have the same end behavior. Now x cubed looks like this. Over here, if you take -1 and cube it, you would get -1, so it looks like this. Almost looks like it's going to be like a line. But if you were to plug in 2, 2 cubed is 8. That means it's accelerating faster than a line, and it's faster than x squared. Looks like this. Remember, we don't call this the vertex. This was known as the inflection point. Inflection point. That's because it doesn't change from decreasing to increasing. It keeps on increasing all the way, but it has this little weird behavior there. All right, next guy is the inverse of x cubed, cube root of x. Cube root. Its shape was was a sideways noodle, not half a sideways noodle. We'll look at that in a moment and think about why that is. It doesn't have a vertex. Just like this noodle, it has an inflection point at the origin. Cube root of 1 is 1. Cube root of -1 is -1. Except for this doesn't rise fast like a noodle. It goes slow, just like a square root. Because the next good number that you could plug in would be 8. Cube root of 8 is 2. Up here, the square root of 4 was 2. So you have to go much farther this way on a noodle to move up. Okay, 1 over x, this known as a rational, because it's made of a ratio. Look, 1 over x, a fraction, also known as a ratio. We decided to call this thing a ninja star. This had a very interesting behavior. Remember that this graph has an excluded value known as the vertical asymptote at x equals 0. So we drew this VA in. VA was at x equals 0 because you can't divide by 0. If I let x equal 0, that would be a problem. In one of your IXL assignments, they're going to ask you for the excluded value. Excluded value is the VA. But it also had a horizontal asymptote. Horizontal asymptote is not necessarily excluded value. It's just what does the graph get really close to when you plug in super large numbers? If you plugged in 100, 1 over 100 would be almost 0. If you plugged in 1,000, it gets even closer to 0, and so on. Now the curve itself looked like this, because if you plug in 1, 1 over 1 is 1. If you plugged in -1, 1 over -1 would be -1. Look like this. This was our ninja star right there. And those were our basic functions. Now, right here, b to the x, this is called an exponential. You learned about this in Math 1 and Math 2. This has a horizontal asymptote. Next week, we're going to go over this graph more in greater detail. But what we could see is that if you let x equals 0, anything to the 0 power would be equal 1. Looks like this. And the graph for an exponential always looked like this. It has a horizontal asymptote. But you're not expected to know this one right now, or not in great detail, and we're going to go over that more. We'll have a lesson next week on this one. Finally, the last one. This is what we're going to be working on all of next week, is exponentials and logs. I'm just going to give you a little preview. a log is the inverse of an exponential. They're inverses. So what would be the inverse of a horizontal asymptote? A vertical asymptote. Oh, by the way, the name of this guy was a logarithmic. If this guy has a key point at 0, 1, then the log its inverse would have a key point at 1, 0. And they just go like this. It's the inverse. Also, going back to here, just as a little reminder, if b is greater than 1, if the base is greater than 1, it's going to be growth. If the base is less than 1, it's going to be what was known as decay. But again, as I said, we'll review that more. Decay means instead of rising up, it would fall down. All right, let's go to the second page of our notes here. And now let's actually look at some transformations of these functions. What this is asking us to do is sketch the parent shape, write the equation in function form, assume that the parent function is f of x, and state the transformations. Well, let's take a look at this. G of x equals x minus 1 cubed plus 4. The parent is a cubic. That means I'm looking at a noodle. Okay? I'm going to state the transformations. I'm going to skip part 2 for now. I'm going to state the transformations. Well, what would this do? Let's just go back to the original parent function. Okay? Original transformation general form. That would be g of x is equal to a times f of x minus h plus k. We did this time and time again last semester. A represents any stretch or compression. H was the left or right shift. K was the up or down shift. Also, if A was a negative, that meant it would flip vertically. So let's see. There is no stretch or compression. This moves left or right. How do we know whether it goes left or right? Well, ask yourself what number would zero this out. Well, if I want this to become 0, I would have to plug in 1. That means you go 1 right, and then this is up 4. You might say, well, how come this one's opposite and that one's not? Well, what if you plugged in 1 here? 1 minus 1 is 0. 0 cubed is 0. 0 plus 4 is 4. That means y equals 4. It's up 4. Now, this part over here gets students a little uncomfortable at times. How do you write the equation in function form? We're just asking you to take it from this and write it as a function form like this. They told us to write the equation in function form and assume the parent function is f of x. So I'm going to say f of x is equal to the parent, x cubed. That means g of x, right here, g of x is going to equal, well, let's see, it has no multiplier. It does have a left-right shift inside of x cubed, so that means it'd be f of x minus 1 plus 4. Look, all you're doing in part 2 here is switching from explicit form to function form. Explicit form is when you actually see the operator cubing in the equation. Function form is when you just rename the operator out here and give it a new name like f for Frank. Let's try this down here. H of x equals negative 3 times absolute value of x plus 1. Well, what is the parent shape? Well, it's an absolute value. That means it's a V shape. What are the transformations? Well, there's a negative here. That means it's been flipped vertically. Or you could say reflected vertically. Either one would be perfectly okay. Multiply by 3. That is a stretch by 3. And then finally, a plus 1 on the outside means it's going to go up 1. Now I'm going to rewrite this. The parent function would be f of x equals absolute value of x. That means that h of x would have to equal, well, let's see, it's going to be in terms of f, no longer absolute value. Well, what's happening to the absolute value? It's being multiplied by -3. So there's -3 times f. Nothing's been added or subtracted in the inside. So there's nothing inside of the function, but then we're adding 1 to the outside of it. It's just translating forms. K of x equals 1/3 x plus 7 squared. Oh, wait, what's going on here? Oh, it's a parent function is a squared. That means it's a parabola. The transformations are, oh, it's been multiplied by 1/3. That means that it's not stretched, it's compressed. Anytime you take a, the absolute value of a, and it's less than 1, it's a compression. So compressed by 1/3. We added 7 to the inside. To zero that out, we would need -7. That means it's left 7. The key point would have been at -7. And then there's no up-down shift. We're going to play this little game again. F of x is equal to, parent would have been x squared. The name of this function is k of x. K of x is equal to, now what's happened to f? It's been multiplied by 1/3. And then we've added 7 to the inside of the function, not on the outside, inside. So x plus 7 goes inside of that function. All right, let's take a look at the next one. Square root. Well, we know that should have a parent shape like half sideways parabola or an eyebrow. This one has been flipped vertically. It has a shift to the right of 4 because we have to zero that out, and it's been moved down 3. Down 3. If we're going to write this in function form, we're going to translate from explicit to function form. The function would have been parent square root of x. The name of this one was r of x, so r of x is going to equal something in terms of f. That's the whole point of these things. We're going to turn it into something in terms of f. Well, what's happened to f? Well, the square root's been multiplied by a negative, so negative f. We have x minus 4 on the inside of the function. Notice it's inside of the operator, and then we're subtracting 3. All right, next step. We have v of x equals 9 cube root of x plus pi minus 100. Wow, how weird. Why would we do that? Because it really shouldn't matter. We should be able to read the math. That's called math fluency. What do I know? It's a cube root. What shape parent is a cube root? Cube roots are always sideways parabola. Pause. It's not a sideways parabola, Mr. Channing. It's a sideways noodle. Multiply by 9, that means it's been stretched by 9. X plus pi, that means it's been moved to the left pi units. You might think that would be hard to graph. No, you just go to the left about 3.14 units, so you put it between 3 and 4 on the negative side, and then down 100. I want to write this in function form. Our parent function would be cube root of x, so f of x equals cube root of x. Then we would write the name of the function, v of x, and we'd say, okay, what's happening to f? It's being multiplied by 9. Is anything added inside of the function, inside of the operator? Yep. X plus pi. And then we have to subtract 100. That's how we translate these. Function form, explicit form. All right, the last one we have here is m of x equals 1 over x minus 6 minus 5.3. Oh wait, that's irrational. That means that's our ninja star. It's going to have a vertical asymptote, it's going to have a horizontal asymptote, and then the parent function is this normal ninja star behavior. Now, what's happened to this? Let's look right here. Inside of the function, it says x minus 6. That means it's been moved to the right 6. What this means with regards to this is, well, what's been moved to the right 6? Everything's been moved to the right 6. In particular, the vertical asymptote would be at x equals 6. Whatever zeroes out the denominator, that is the x value of the vertical asymptote. It's also been moved down 5.3. Well, what's going to get moved down 5.3? Well, basically everything's going to get moved down 5.3, but especially the horizontal asymptote is going to move up or down, in this case, down 5.3. So the horizontal asymptote is at y equals 5.3. Remember, when we learn this, VAs are always x equals, and horizontal asymptotes are always y equals. Now, going back here, what would be the way to write this from explicit to function form? Well, we're going to say the parent function was 1 over x. Our original is m of x. Well, what's happening to the function? Is anything multiplied on the outside? Nope. Has anything been added or subtracted on the inside? Yeah, x minus 6. And then we have subtracted 5.3 from the outside. And that is how we translate these guys. All right. Next up. What we have now is we've got the same type of processes, but we're reversing the way it's written. It's now been written in function form, and we would like to write it in explicit form. Now, what can we see here? We can see we have a function that's been moved to the right 6 and up 9. Well, what kind of function is it? If I didn't write this over here, you wouldn't be able to know. But here it's telling you that it is a square root. That means the parent shape is half sideways parabola. I want to write the equation in explicit form. Well, let me go back here and look at the transformations. It's moved to the right 6, up 9. We can just read it right off of there. Right 6, up 9. Now, they want us to write the equation in explicit form. That means put the operator in there. Well, what's the name of this function? It is g of x. What kind of function is it? It's a square root. Has this square root been multiplied by anything? Nope. Has it been flipped? Nope. Has it been moved left or right? Yeah. Right 6, up 9. That is explicit form. It's literally reversing the process we just did. Let's take a look right here. Number 2. I have h of x equals negative 2 times f of x minus 4, and the function is supposed to be a cubic. Oh, that means the parent is a noodle. It also means that it's been flipped vertically. It's been stretched by 2. And it's down 4. I want to write this in explicit form. Well, the operator, instead of writing it as f of x, is going to be something in terms of cube. Well, it was called h of x, and I have a cubic. What's happened to this cubic? Well, it's been multiplied by negative 2. So negative 2. Nothing's been added or subtracted to the inside. So I didn't really need to write it like this with this parentheses here. But I was being silly. I wasn't looking ahead. So I have negative 2 times x cubed. Notice nothing's on the inside. But then I have to subtract 4. Let's just check this. Does this really have a flip vertical, a stretch by 2, and a down 4 for a noodle? Well, it is a noodle. It's been flipped, it's been stretched, and it's been moved down by 4. There we go. Next one. G of x equals 1/3 of f of x plus 2. And we know f of x equals absolute value of x. That means it's going to be a V shape. We read the transformations. We can see that this is going to be compressed by 1/3. We can see it moves left 2. It's left 2 because you have to zero this out. So it would be negative 2, left 2. If I want to write this in explicit form, what I know is I don't want to write it in terms of f. I want to write it in terms of absolute value of x. Let's see. Absolute value. Has the absolute value, has the function been multiplied by anything? Yes. 1/3 times x. Has anything been added or subtracted on the inside? Yes. X plus 2. On the outside? No. If I go back and check this, let's see. Well, this has a compression of 1/3. Yep. You would need negative 2 for x. In other words, it's got to move to the left 2. And there's nothing going up or down. There we go. All right, last guy. 5 times f of x minus 3 plus 19, and f of x equals 1/x. That means we have a ninja star. Remember, 1/x means you have a ninja star. Let's see what our compressions are, or stretches, or flips, or transformations, all of it together. Multiply by 5. That means it's stretched by 5. X minus 3. That means it goes to the right 3. That means the VA would be at x equals 3. And then it goes plus 19. That means it's up 19. That means the HA would be at y equals 19. Now, if I were to write this in transformation form, in explicit form, because it's already in function form, I'm going to write g of x is equal to 5 times 1/x minus 3 plus 19. The reality is most people wouldn't write 5 times this. They would just multiply 5 times this function and rewrite it. So most people would write it as 5/x minus 3 plus 19. Notice I only multiply 5 times the top. That is how we rewrite and read graphs. Now what we want to do is we want to be able to take a graph and find everything we can about it. So let's see, what can we see about this? parent function. If I look at this graph right here, it's very clear this is a parabola. So the parent function is quadratic. It's going to be f of x equals x squared. Now let's try to figure out what the transformations are. I can clearly see that this guy has been flipped vertically. It's upside down. The vertex is no longer at the origin, it's up here. It's moved to the right 1, 2, 3, right 3. It's been moved up 1, 2, 3, 4, 5, 6, 7, 8, 9, up 9. That means, well, let's see, has it been stretched? If I go to the right 1, it's down 1. If I go to left 1, it's down 1. Let's see, if it's a squared function, then if I go to the right 2, it should go down 4. Let's see if that happens. 1, 2. 1, 2, 3, 4. Yep, sure looks like it's got a normal stretch factor. That's telling me that the equation ought to be f of x is equal to negative x minus 3 squared plus 9. Let's see, does that have all of the components that we can read here? It's a parabola. It's been flipped vertically. It goes to the right 3 and up 9. Yep. All right, now we're going to look at the intervals. We're going to just review intervals. We haven't done that for quite a while. Domain. How far to left and right does this graph go? It goes all the way from negative infinity to infinity. X is an element of negative infinity to infinity. The range. How high and low does this graph go? Well, it clearly goes all the way down to negative infinity, and the highest it ever goes is 9. Y is an element of. The lowest value here is negative infinity. The highest value is 9. Excuse me. And it actually does get to 9. So we include 9. Increasing. Where is this graph rising as we go left to right? Well, if we start out at negative infinity, this graph is clearly rising all the way until it gets to this x value. So it's increasing from negative infinity all the way to the x value here, which was 3. And then it's decreasing all the way from this value all the way until the end of the x values. So it's decreasing from 3 to infinity. We can see that it's rising all the way here. Rising, it's increasing. So from negative infinity until 3, and then it starts decreasing from this point on. Remember, increasing means rise, decreasing means fall, and you have to read this from left to right. The last little piece we have here is positive and negative. That means when is it above the x-axis? Negative means when is it below? Well, is this graph ever above? Well, clearly it's above from here, which is x equals 0, all the way to here, which is x equals 6. So it's positive from 0 to 6. Notice we don't include 0 or 6 because when x is 0, y is 0, and that's not positive. When x is 6, y is 0, that's not positive. Now, is it ever below the x-axis? Yes, we can see it's below the x-axis all the way from negative infinity to 0. Look, the whole graph is going to be below. So from negative infinity to 0. But then it starts being below again over here at 6. So union 6 until you get all the way out here. Now this is always a little tricky. I know it's pointing down, but the x value over here is positive infinity. That's why it was from 6 to positive infinity. This was all just a review of interval notation that we have done many times before in class. Okay, let's take a look at the last page of notes that we have here. And we're going to look at this. What is our parent function? Well, what does this appear to be? Looks like a noodle. That means f of x is equal to x cubed. Can we see some transformations? If you look at the notes page, and by the way, if any of this looks a little blurry to you, that's why I have actually given you the notes that you could follow along with and print out, because sometimes the camera is just going to be a little bit blurry here. Just the nature of the technology that I'm dealing with. But we can see, if you look at the actual physical handout, that this point right here was, I'll write it larger, -4, 1. We can also see the noodle is upside down. So that means it's been flipped vertically. It's been moved to the left 4. It's been moved up 1. Now the next thing I'm going to try to do is check, is there any stretch factor to this? Well, this point right here is -3, 0. That means it went to the right 1 and down 1. From 1 to 0 is down 1. There is no stretch factor. So let me write the equation here. The equation would be f of x is equal to, I've got a noodle that's been flipped, so that means it's negative. I have a noodle that's been moved to the left 4, so that'd be x plus 4 cubed. Notice if I plugged in -4, it would zero it out. But then up 1. Let's see, is this a noodle? Yes. Has it been flipped? Yes. Would this make it go left 4? Yep. And up 1. Now let's look at the domain. How far does the noodle go left and right? All real numbers. How far does the noodle go up and down? Again, all real numbers. Where is this increasing? Remember, we have to read the graph from left to right. Is this graph going up or down at all? Well, if I start over here at -infinity, it's just dropping, 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 keeps on dropping, stops for a second, but it keeps on dropping. That means it's dropping, it's falling everywhere. It's decreasing always. So where's it increasing? Nowhere. And the way we would write that is x is an element of nothing. Okay, is it positive or negative? Well, is it ever above the x-axis? Yes, it's above the x-axis from -infinity till you get to -3. So -infinity to -3. Is it ever below? Yeah, from -3 all the way for the rest of the x values. So from -3 to infinity. Now I'm just going to show you another way that when you do IXL assignments, instead of writing it like this, they might write it like this. They might use something like this. X such that x is greater than -3. They might use this inequality notation. Just be prepared for that. It means the same exact thing. All right, last two problems that we have is two sketching problems. What do we've got here? We've got a absolute value, so it's a V shape. What can I see about it? I can see that its vertex is at 4, because that would zero that out, comma 3. So I'm going to go over here, 1, 2, 3, 4, up, 1, 2, 3. It's been flipped vertically and it has no stretch factor. That means I should go to the right 1, down 1, to the left 1, down 1. And then I can continue on this pattern, or I could make a table of values, but I can keep this pattern because it's an absolute value. It's a bent line. And it should look like this. But I could make a table of values. I could say, oh, what happens when x is 5 plug in 5. 5 minus 4 is 1. Absolute value 1 is 1. The opposite of that is negative 1. Negative 1 plus 3 is 2. I could go 6. 6 minus 4 is 2. Absolute value of 2 is 2. The opposite of that would be negative 2. Negative 2 plus 3 is 1. And so on. I could see this pattern. Now, domain and range. What's the domain of this? Well, it goes all the way from negative infinity to positive infinity. It's all real numbers. What's the range? Well, it does go down to negative infinity, but the highest y value is right here. That y value was 3 inclusive. Is this thing ever rising? Is it increasing? Well, clearly it's increasing as we go from left to right, all the way from negative infinity, from the left side, until you get to this x value. That x value is the vertex, which was 4. And it's decreasing from 4 until you get to the end of the x's, which would be infinity. Is it ever above the x-axis? Well, this is where it'd be important to find the x-intercepts, which is what I did by just keep on graphing that table or that pattern, and that was from 1 to 7. 1, 2, 3, 4, 5, 6, 7. From 1 to 7, it's above the x-axis. Let's just verify that. If I plug in 1, 1 minus 4 is negative 3. The absolute value of negative 3 is 3. The opposite of that would be negative 3. Negative 3 plus 3 is 0. Yep. And if I plug in 7, 7 minus 4 is 3. Absolute value of that is 3. Minus 3 plus 3 is 0 again. Those are the two x-intercepts. Is it ever below the x-axis? Well, it's all the way from negative infinity until you get to 1. Negative infinity to 1, it's below. Or from 7 to infinity, it's below. So that's how we graph that. But this is all old hat. This is all transformation of stuff we've done many times. All right, last one we have is, what do we got going on here? Well, we have the cube root. The cube root was a sideways noodle. The key point, and in noodles, we don't call it a vertex, we call it a inflection point, was, let's see, x plus 4. So negative 4 minus 1. Negative 4 minus 1. So I'm going to go 1, 2, 3, 4, down 1. There's our key point. It does have a stretch of 2, but I'm really not sure. Let's see. That means if I go to the right 1, I should go up 2 like this. If I go to that left 1, I should go down 2. It should look like that. So it's kind of a stretched out sideways noodle, like such. Well, let's see if we can figure out what the domain of this. Well, look, for every noodle, the domain is super basic. It's always all real numbers, even if it's sideways. And the range is also going to be all real numbers. Now I just have to decide increasing and decreasing. Well, is this thing increasing or decreasing? It's increasing forever from negative infinity to positive infinity. So it's increasing on all real numbers, or negative infinity to positive infinity. It's never decreasing. So I'm going to go x as element of never. Is it ever above the x-axis? Yes, right here. But what is that value? Let's see. The key point was at negative 4. If I plugged in negative 3, let's see. Negative 3 plus 4 is 1. The cube root of 1 is 1. Times 2 is 2. 2 minus 1 is 1. Wait a second. So our key point is somewhere in between -4 and -3, because at -4, y is -1. At -3, y is +1. That means the x-intercept has to be somewhere right here. Well, what is that value? Well, let's just try to solve for that. That would be when y equals 0. So I'm going to let y equals 0 to find this. 0 equals 2 times the cube root of x plus 4 minus 1. I would add 1. Divide by 2. So I get 1/2 equals cube root of x plus 4. I'm going to work over here. I would have to cube both sides. Well, what's 1/2 cubed? That'd be 1/2 times 1/2 times 1/2. That'd be 1/8 equals x plus 4. And then I would subtract 4. Well, that's -4 plus 1/8 equals 8 equals x. -4 plus 1/8 equals x. That would just be -3 and 7/8 equals x. Or you could write it as a decimal. So it's going to be positive from -3/7, -3 and 7/8 all the way out to infinity. -3 and 7/8 all the way to infinity. And it's below the x-axis from -infinity to -3 and 7/8. And that is the last of our examples. Bunch of review, combining a lot of skills. Now you're going to be asked to go do some IXL practice related to this stuff. It's going to be little individual pieces of this. Remember, you don't have to, you're not expected to get to 100% when you do IXL. You go as far as you want, and don't forget to look back at the sliding scale for our grades on IXL to determine what's appropriate. There's also examples built into IXL and explanations if you ever get a problem wrong. All right, good luck on your assignment and have a great day.